Welcome to the screencast video on reversible reactions, and we're going to have a quick little video here about what actually are reversible reactions or equilibrium reactions. You can see here on the screen I've got different examples of equilibrium reactions that are around us. So the most common one that you're probably aware of is the one down here that's been partially covered by my face, and that is the acetic acid equilibrium. You can see down the bottom here that we've got acetic acid, and when that is dissolved in water, it dissociates or breaks apart to give you the ethanoate ion and also the hydronium ion. And that can go from left to right, but also from right to left. Now, it's a very, very weak acid, and when you watch the videos on strong and weak acids, you'll realize that most of the form exists in this form here. Okay, so a large percentage, maybe 98% or so of all the acetic acid exists in the molecular form here, and not very much in the ionized form, because it's a weak acid. It's a very it doesn't dissociate very much. Okay, let's have a look up here towards the top left, and we can see that we've got the equilibrium reaction that occurs inside our blood, where you've got the hemoglobin here combining with oxygen to give you oxyhemoglobin, and then of course up in the lungs that is favored towards the right hand side, and we'll find out why in future videos. But then when it gets to the site of need, let's say a leg muscle that's undergoing exercise, it will then be favored towards the left hand side and deliver oxygen. So that reaction can go backwards and forwards. We've got the industrial example down the bottom here with ammonia production in the formation of ammonia, and we're going to do a whole video on that about the Haber process and find out the importance of that reaction. So what is a reversible reaction? Well, think of this one here where we've got hydrogen and iodine, and they react together to give you hydrogen iodide. It's a reaction that can go both ways, but it's what's known as a dynamic system. In other words, it goes backwards and forwards continuously. The forward reaction occurs and the reverse reaction occurs, and the rate at which those occur is different depending upon the equilibrium system you're talking about. But when it's at equilibrium, that means that their concentrations don't change, and we're going to see that very, very soon. So let's get a closed container. Let's get some hydrogen and iodine, put it in there, and what's going to happen is they're going to start to react. And you can see in this graph here that at time 0, that up the top we have our reactants, hydrogen and iodine, and they start to react to form the products according to the reaction you can see in the top here. Now, because they're being used up, their concentration is decreasing per unit time. At the same time, the concentration of hydrogen iodide is going up. So what we're seeing here is we're seeing that the forward reaction, where the reactants are combining to form the products, we're seeing the forward reactions occurring because the concentration of the reactants are going down and the hydrogen iodide is going up. Now, of course, that's going to keep going until we reach a certain point, and you can see here at this time right here, the concentration is stable. It's not changing anymore. So what's happening is the forward reaction's going towards the right and the reverse reaction's going towards the left, but it's reached a state of dynamic equilibrium. The concentrations of those reactants and products are no longer changing. Okay, and so by definition, a dynamic equilibrium for a chemical reaction is the condition in which the rate of the forward reaction equals the rate of the reverse reaction. Right, so let's just think about this, how you could demonstrate this in a lab. Well, let's say you have two containers, okay, and on the left here you have some colored water which represents the reactants, and then the bowl on the right hand side represents the products, okay, hydrogen iodide. So initial, what's going to happen is that the forward reaction is going to be very fast. There's going to be no backward reaction because there's no products, right? So the reverse direction is going to be 0, and the concentration is going to be 0. And so we can see that with the graph here, that at time 0 for our hydrogen iodide, the product is 0. Then what happens is the reactants combine to form the products, and you can see some water's been moved from the first container into the second container. So the concentration of the reactants are decreasing. You can see that here, the volume is decreasing. Whoops. The volume is decreasing. And so we can see this with the graph. The concentration of the reactants are decreasing, but the product side is increasing. And we can see that here on the right-hand side, where you can see that there's some hydrogen iodide being represented. Then as time keeps going on, the reaction rate starts to slow down because it's getting closer to equilibrium, and you can see that the curves show that, right? We have a very steep curve here at the beginning, so the concentrations are changing rapidly in large amounts per unit time. However, as time's going on, you can see that their concentration is not changing to the point when we get here that there is no change in concentration. And so what we're saying here is that the forward reaction is equal to the reverse reaction, and their concentrations are constant. When we get that, it's called equilibrium. It's at equilibrium. Now, a very famous chemist that we're going to be learning more about this is called Henri Le Chatelier. And so he studied chemical equilibria and came up with the principle that is the foundation for describing how systems respond when their conditions are changed. So if we have an equilibrium reaction and we change the conditions, that reaction will respond in a certain way, and it's known as Le Chatelier's principle. So if we read it, it sounds very long, but let's just dissect it out a bit. If a system is equilibrium and a change is made that disturbs the equilibrium, then the system responds in such a way as to counteract or oppose the change, and then a new equilibrium is established. Okay, so we're going to learn in the next video, if we disturb an equilibrium system that's already at equilibrium, it will respond in a way to try and minimize that change and return it back to a new equilibrium. Now there's three things that can affect equilibrium: temperature, concentration, or actually there's four, but that one's not up there. We forgot catalysts. So temperature, concentration, and pressure, and of course catalysts. And pressure is related to volume, right, when we're dealing with gases anyway. And so volume and pressure are very, very similar in terms of that. So anyway, that's the quick video. Hope you know what equilibrium is, what we mean by dynamic equilibrium, and that the concentrations start off very high for our reactants, start off from 0 for our products, and they slowly change until there's no change in concentration. At that point, we have equilibrium. And then we have Le Chatelier's principle, which describes, for an equilibrium system, the change in that system results in a new change and a new equilibrium. Okay, see you in the next video, and keep having fun with your chemistry.